A related rates problem is when you have two quantities whose rates of change are related. You know the rate of change of one of the quantities, and you want to find the rate of change of the other quantity. Let's take a look at an example. Suppose a coffee filter is in the shape of a right circular cone with base radius 3 centimeters and height 6 centimeters. If hot water is dripping out of the filter at a rate of 0.1 cubic centimeters per second, what is the rate at which the water level is falling when the water is 0.2 centimeters high? Okay, here we have the cone. It has a height of 6 and a radius of 3. Okay, the blue part is the actual water, okay, and it has a height. Let's call it h. So let's just write this here, h, and it also has a radius. Let's call it r. The formula for the volume of a cone is given by 1/3 pi r squared h, where r is the radius and h is the height. Now we're going to apply this formula to the blue cone here, where r is the radius and h is the height. Okay, we know that the change in volume with respect to time is given by negative 0.1. Okay, because we're told that the hot water is dripping out of the filter at a rate of 0.1 cubic centimeters per second. Okay, and we put a negative sign here because the water volume is decreasing. Okay, so that's what we know so far. We want to find dH dt. Okay, that's the rate at which the water level is falling. Okay, the water level is h. Okay, we want to know the rate at which that's changing, so that's just a derivative. So we want to find dH dt, but we want to find that when the height is 0.2 centimeters. So we want to find that when h equals 0.2. Okay, now let's look here. Notice we have a big triangle and then we have the smaller triangle for the blue part. Okay, using similar triangles, we have the ratio given by h, the little height to the little radius, is equal to the big height, 6, to the little, the big radius, 3. Okay, so the ratio between the little height and the little radius is the same as the ratio between the big height and the big radius. Okay, so that's equal to 2. So h equals to 2r. Solve for r. So we get h over 2. Now the volume is 1/3 pi r squared h. Okay, so plug in what we got here for r. Multiply by h. Okay. And multiply this out. This is what we get. Okay, so V equals pi over 12 h cubed. Here, notice we got V in terms of h only. Before, the volume was in terms of r as well as h. But by using this here, we were able to write r in terms of h. And so we plugged it in here and we found this expression in terms of h only. So that's good. Now from here we're going to differentiate both sides using implicit differentiation. Okay, so v and h are both functions of t, and we're going to differentiate with respect to t. Okay, so that's pi over 12 times, drop the 3, so that's 3h squared, times the derivative of h. That's by the chain rule. Okay, we already know dv dt. That's equal to negative 0.1. And we want to plug in h equals 0.2. Right, because we want to find dh dt when h equals to 0.2. Okay, so I'm going to plug in (0.2) for h. Okay, so now I get negative 0.1 equals to pi over 4 times 0.2 squared dh dt. Okay, so let's solve for dh dt. Okay, so multiply both sides by 4 over pi. Divide by 0.2 squared. So we isolate dh dt. Okay, and you can plug this into a calculator. It's approximately minus 3.18 centimeters per second. Okay, so that's how fast the height is changing when h equals to 0.2. It's about minus 3.18 centimeters per second. If you look back here, solve for dh dt, you'll get negative 0.1 divided by 3h squared times 12 over pi. Okay, and here notice that as h gets smaller, the denominator here gets smaller. So this whole expression gets bigger. So that means that the dh dt is it's getting bigger, but it's negative. Okay, so the height of the water falls faster as the height h gets smaller.